Welcome to this lecture on the history of artificial intelligence. This lecture will begin with some high-level discussion of artificial intelligence philosophy, and then dive into a tour of artificial intelligence history up through the time of this recording in January of 2026. This will include AI early imaginings, gestation, birth, early enthusiasm, a dose of reality, knowledge-based systems, AI becoming an industry, AI adopting the scientific method, the emergence of intelligent agents, the age of big data, the deep learning revolution, and the generative era. Let's get started with a little philosophical discussion. The word for our species, Homo sapiens, translates to man the wise, and this alone reflects the importance that we put on our own intelligence as a species. For thousands of years, humans have sought to understand how we think, including how we perceive, understand, predict, and manipulate a world far larger and more complicated than ourselves. But the scientific field of artificial intelligence goes further. It's not just asking whether we can understand how we think, which is a challenging enough problem in itself, but also how can we build intelligent entities separate from ourselves. You probably don't need any convincing that the field of artificial intelligence is a pretty exciting area of study. Stuart Russell, a prominent authority in the field of artificial intelligence, once stated that molecular biology and artificial intelligence are most regularly regarded as the fields I would most like to be in by scientists in other disciplines. As a relatively new field, and in contrast with some older fields, there's still much to be discovered and invented in the context of artificial intelligence research. AI also encompasses and overlaps with a huge variety of subfields. Another quote by Stuart Russell says, "AI is relevant to any intellectual task. It is truly a universal field." So what are some of the questions that have driven or inspired the advancement of artificial intelligence across different fields of study? Philosophy has asked questions like, can formal rules be used to draw valid conclusions? How does the mind arise from a physical brain? Where does knowledge come from, and how does knowledge lead to action? Mathematics has asked, what are the formal rules to draw valid conclusions? What can be computed? And how do we reason with uncertain information? Economics has asked, how should we make decisions so as to maximize payoff? How should we go about doing this when others may not go along? And how should we do this when the payoff may be far in the future? Further, neuroscience asks, how do brains process information? Psychology asks, how do humans and animals think and act? Computer engineering asks, how can we build an efficient computer? Control theory and cybernetics asks, how can artifacts operate under their own control? And lastly, linguistics asks, how does language relate to thought? We can use a few key terms to help us categorize different ways of defining and thinking about artificial intelligence. These include thinking versus acting, and humanly versus rationally. Thinking is all about process and reasoning, while acting is all about behavior. The qualifier humanly refers to the fidelity of some performance being like a human. The qualifier rationally refers to doing the right thing given what is known. Armed with these terms, let's look at 4 categories of artificial intelligence definitions. The first is thinking humanly. This focuses on the cognitive modeling approach where we're trying to create machines with minds that can follow the same internal logic, decision-making processes, and intuition as a human brain. This is also the definition where we think of AI potentially achieving consciousness or being able to be truly creative or inventive. The second is thinking rationally. This focuses on logic and laws of thought. It assumes that there's a correct way to think using the laws of syllogism and formal logic. For example, if A equals B and B equals C, then we can conclude that A equals C. We can think of deductive algorithms that rely on strict logical inference, such as expert systems, to fall under this definition. The third is acting humanly. This focuses on whether a machine can behave or perform a task in a way that is indistinguishable from a human. successfully acting human can occur regardless of whether the internal thinking of the AI is actually human-like. Under this definition, we can think of things like chatbots and robots that are designed to communicate or interact in a way that seems human. This is the definition that the Turing test explores, which we'll talk about a bit later. The last definition is acting rationally, which largely focuses on agents, which are entities that can perceive, persist, adapt, create, and pursue goals. And here the focus is getting agents to achieve the best outcome, or the best expected outcome in uncertain environments. This area is also where we would think about the most traditional forms of machine learning, such as supervised, reinforcement, and unsupervised learning. This figure expands upon these AI categories, seeking to connect them with other related fields or subfields. It also includes some key individuals from history whose work and views aligned with these certain categories. For example, Aristotle explored thinking rationally, Alan Turing explored acting humanly, and Newell and Simon explored thinking humanly. We'll see all of these individuals mentioned in upcoming slides. When it comes to scientific pursuits, I think it's reasonable to say that most of the work that has and is being done has focused on either thinking rationally, acting rationally, or acting humanly, in part due to the ethical concerns and philosophical dangers of potentially creating a conscious, self-aware superintelligence that would fall under the domain of thinking humanly. Now let's begin our tour of artificial intelligence history with early imaginings, spanning from 700 BC to 1950 AD. Back around 700 BC, the Greek poet Hesiod wrote about Hephaestus, otherwise known as Vulcan, the god of fire, invention, and blacksmithing. In this mythology, Hephaestus created Talos, a bronze humanoid automaton. Talos was tasked to protect the island of Crete. He circled the island's shores 3 times daily and hurled boulders at approaching enemy ships. At his core, Talos had a tube running from his head to his feet that carried a mysterious life source of the gods that the Greeks called Ichor. And if you're as old as me, or simply love aging movies, you might remember this scene from the 1963 movie Jason and the Argonauts, where the main characters are being pursued by Talos. This Talos character, given a little poetic license, shared some similarities to the modern conceptualization of a robot, driven by an artificial or supernatural force. Also in Hesiod's theogony, the god Zeus tasked the god Hephaestus with creating Pandora, an artificial evil woman, who was sent to Earth to punish humans for discovering fire. On this vase, we can see an image of Pandora, where she's striking a pose that looks suspiciously rigid and artificial compared to the other individuals pictured. This is a really interesting book called Gods and Robots, which talks about artificial beings in mythology. From this book, Adrian Mayer says that it could be argued that Pandora was a kind of AI agent, where her only mission was to infiltrate the human world and release her jar of miseries. At the bottom of this slide, there's also a link to a separate video about this book and topic of myths, machines, and ancient dreams of technology that you can go and check out. Again, in Hesiod's theogony, the term biotechny also emerged, which means life through craft, or referring to something that was made rather than born. As an interesting side note, later in 1919, the Hungarian agricultural engineer Karl Erecki introduced the term biotechnology in his book to describe the process of using technology to convert raw biological materials, like livestock and plants, into socially useful products. Also from this mythology, the god Hephaestus created a number of other biotechny entities, in addition to Talos, including his golden personal assistants, which were automata endowed with strength and reason, a drone-like eagle that would torment Prometheus, which was programmed to come and tear out his liver each morning after it had regenerated the night before. Also, fire-breathing bronze bulls. Yoking these bulls was part of Jason's impossible tasks in his quest to obtain the Golden Fleece. And in addition to Talos, Hephaestus also created Laplace, which is a golden mechanical hound that was also tasked with protecting the island of Crete. And yet another example is the invincible autonoma army that Jason had to defeat. These automata sprang from dragon's teeth and were programmed to attack the nearest target, To defeat these automata, Jason essentially had to develop the first programming hack. By throwing a rock at one of the automata, he was able to get them to start attacking each other. Starting in the early ADs, realistic humanoid automatons were assembled by craftsmen from every civilization. This included the Hero of Alexandria in 70 AD, which was an entirely mechanical play almost 10 minutes in length, powered by a binary-like system of ropes, knots, and simple machines that were run by rotating a cylindrical cogwheel. In 1200 AD, Ismail al-Jazari created an automated robot band, as well as automated moving peacocks, which were driven by hydropower. In 1780 AD, a French watchmaker named Pierre Jacques-Dreux designed and built a series of animated dolls. And in 1800, a Hungarian author and inventor named Wolfgang von Klempen created the Turk, which was a chess-playing automaton hoax intended to convince people that they were playing chess against a machine, when in fact it was being controlled internally in secret by a hidden person. The Middle Ages birthed rumors of secret, mystical, or alchemical means of creating life by placing mind into inanimate matter. This included stories of the homunculus, which were miniature, fully formed humans created through alchemy. Another example is the golem, coming from late 16th century Jewish folklore. The golem was a legendary humanoid figure animated from clay or mud by mystic rituals, most famously created by Rabbi Judah Loew to protect the Jewish community. The golem was animated by writing emet, the Hebrew word for truth, on the entity's forehead as a sort of activation code. It could later be deactivated by erasing the first letter of emet, changing the word to met, meaning dead. This was perhaps one of the earliest recorded cultural representations of a logic-based override or deactivation code. The earliest science fiction brought about ideas of artificial men and thinking machines. One of the earliest was Frankenstein's monster, from Mary Shelley's book Frankenstein from 1818. This work was considered the first true science fiction inspired by the story of the Titan Prometheus, who most of us recognize from mythology as the god who stole and gave fire to mankind, but who was also credited with the creation of humanity from clay. In 1920, Rossum's Universal Robots introduced the world to the word robot and furthered the genre of science fiction. However, robots and robotics really took off thanks to Isaac Asimov's 1945 book, I, Robot. In this book, he introduced the world to the 3 laws of robotics, including don't harm humans, obey orders, and protect yourself. This comic suggests what can happen if these laws are not applied in the correct order of priority. Now we'll move on to artificial intelligence gestation, from 350 BC to 1950 AD. Chinese, Indian, Arabic, and Greek philosophers all developed structured methods of formal thought that would lay the foundations of formal reasoning. Aristotle could be credited with the earliest formal contributions to artificial intelligence, in giving us a formal analysis of the syllogism, which is a critical founding element of logic. Around 300 BC, Euclid wrote the book Elements, which was instrumental in the development of logic and modern science. In 1820, Al-Khwarizmi developed algebra, and his own name, mistranslated, later evolved into the word algorithm to describe step-by-step procedures like the ones he outlined for performing arithmetic. In the late 13th century, Ramon Lull pioneered computational theory, proposing that reasoning could be performed by a mechanical process. He developed several logical machines for producing knowledge, including this one you see here on the right. He was later described as the grandfather of computer science. And around 1700 AD, the engineer Gottfried Leibniz proposed that human reason could be reduced to mechanical calculation. He was one of the first to realize that a binary digit system could be used to represent any complex information as a mathematical alphabet, and envisioned a future with physical thinking machines. The term prediction refers to a statement about a future event or outcome. Robert Fitzroy was an English officer of the Royal Navy and a scientist in the mid-19th century. He was also a pioneering meteorologist, and he made accurate daily weather predictions, as well as coined the term forecast. Furthermore, the invention of several types of barometers were also attributed to him. Across the 19th and 20th centuries, mathematical logic yielded essential breakthroughs that ultimately made AI seem plausible. Some of the most important work includes George Boole's The Laws of Thought, where he tried to go over, under, and beyond the logic that Aristotle had previously laid out. Also, Friedrich Frisch wrote Begriffsschrift, a formal language of pure thought that laid the groundwork for early logic notation. Russell and Whitehead wrote the Principia Mathematica, which popularized symbolic logic and formalized a number of mathematical propositions. And David Hilbert challenged mathematicians to answer the question, can all of mathematical reasoning be formalized? Some key work in the 1930s helped us to understand some of the computational limits or boundaries of what we could expect AI to achieve in the future. In 1930, Kurt Gödel offered the completeness theorem, which showed that in first-order predicate logic, all true statements are derivable. He also proposed the incompleteness theorem, which basically showed that there were limits on what you could do with deductions. In 1937, Alan Turing described the halting problem, where, if you had some computer program and an input, the question was, can you decide if that program will finish running within some specific amount of time, or will it run forever? Turing basically showed that no such program can exist. This is crucial because it identified a limit for intelligent programs. In other words, there will never be a universal program verification system, or a system that can look at a program and say, are you expected to finish in some time less than infinity? In 1943, work by Pitts and McCullough laid the groundwork for neural networks. This was recognized as some of the first true AI research. In developing neural networks, they drew parallels between the brain and computing machines, and they created a computational model for the architecture of neural networks. However, these early neural networks were simply linear threshold gates with pre-assigned weights that were designed to automatically make predictions given some input. So, unlike the neural networks of today, these systems weren't doing any learning. In 1951, Minsky and Edmonds developed a neural network machine they called SNARC, which stands for Stochastic Neural Analog Reinforcement Computer. This was the world's first synthetic neurocomputer, made up of 3,000 vacuum tubes, simulating 40 neurons that sought to simulate a rat trying to navigate a maze. Going back to Alan Turing and some of his most famous work, in 1950, Turing first defines machine intelligence using what became known as the Turing test. He also wrote about learning machines, genetic algorithms, and reinforcement learning. And he proposed the child program idea, which suggests that if you want to produce a simulation of an adult mind, why not start by producing a simulation of a child's mind, and then having it learn and grow into that of an adult one? The Turing test in particular was a test of a machine's ability to exhibit intelligent behavior equivalent to or indistinguishable from that of a human. This refers back to the AI category of acting humanly that we discussed at the start of this lecture. The Turing test was inspired by the imitation game, which was a party game where you had player C, the interrogator, who is trying to determine the sex of two players that he can't see. One is male, pretending to be a female, and the other is a female. In Turing's original test, the challenge was the same, but player A was a machine taking on the role of a male pretending to be a female. The test asks whether the interrogator would decide wrongly as often when the game is played using a computer as opposed to when there's a human male in this role. The interrogator is meant to assume that both players A and B are both human, and has no knowledge that the role of player A could be taken by either a computer or a human. This test was not specifically designed to determine whether a computer is able to fool an interrogator into believing that it's human, but rather whether a computer could imitate a human. Today, there's a different standard interpretation of the Turing test. In this version, which you've probably heard about, player A is a computer and player B is a person of either sex. Here, player C knows that one of the other two players is a computer and is trying to decide which one is human and which one is a machine by asking questions and receiving natural language responses. There are important differences between these two types of Turing tests. Specifically, the original test requires the resourcefulness associated with intelligence, not just the ability to simulate human conversational behavior. This has led to some controversy over whether these two versions are equivalent and whether new standards for evaluating machine intelligence are needed. Now we move on to the birth of AI in 1956. While working at IBM in 1955, Arthur Samuel built a program that learned to play checkers at a strong amateur level, disproving the idea that a computer can only do what it's told. In 1956, this program was demonstrated live on TV, and in 1959, the term machine learning was coined. The first artificial intelligence workshop was organized by John McCarthy and held at Dartmouth College in 1956. This was a 2-month workshop involving 10 attendees, including Marvin Minsky, Claude Shannon, Nathaniel Rochester, Arthur Samuel, Trenchard Moore, Ray Solomoff, Oliver Suffrage, Alan Newell, and Herbert Simon. While this workshop didn't yield any major breakthroughs, it brought together the major figures of AI research, and 20 years later, the field of AI is dominated by their academic ancestry. Many of these researchers went on to have successful careers at institutions like MIT, Carnegie Mellon, Stanford, and IBM. And it was at this workshop that the term artificial intelligence was coined and was defined as the science and engineering of making machines intelligent. In 1956, Simon and Newell developed the logic theorist, or LT, which was the first program engineered to mimic the problem-solving techniques of a human being using logic gates, and it was considered to be the first artificial intelligence program. Eventually, the logic theorist proved 38 of the first 52 theorems in the Principia Mathematica. It also found new and more elegant proofs for some of this work, and ultimately was submitted to the Journal of Symbolic Logic, including the logic theorist as an author. But this paper actually got rejected, with the reviewers citing that a new proof of an elementary mathematical theorem was not notable. Of course, the reviewers unfortunately missed the intriguing point of this work. The logic theorist program led to a number of important advancements. First, it explored reasoning as search. This LT program utilized a search tree where each branch was a deduction based on the rules of logic. Within the search tree, a leaf node at the bottom could be picked as the goal, or the proposition to be proved, and the pathway leading to that node was a proof of that proposition. Here, a proof is a series of statements deduced using logic, leading from a hypothesis to the proposition to be proved. Another important advancement was their exploration of heuristics. Simon and Newell realized that these kinds of search trees could grow exponentially depending on the scale of the problem. And in order to effectively search the tree, they needed to trim branches that were unlikely to lead to a solution. These strategies led to the coining of the term heuristics, or ad hoc rules. Heuristics ultimately became very important to overcome intractable combinatorial explosions in search, or in other words, when the problem space became far too large. Lastly, this work contributed to list processing. Specifically, to complete the logic theorist work, they developed a programming language called IPL. This used the same form of symbolic list processing that later formed the basis of the well-known Lisp programming language. Now we head into the years of AI early enthusiasm, from 1956 to 1969. At this point in history, we were at one of the earliest peaks of artificial intelligence research, marked by great enthusiasm and expectation. However, researchers of the time were limited by primitive computers and programming tools. While working at MIT in 1958, John McCarthy invented the aforementioned Lisp programming language, which was a high-level programming language. A high-level programming language allows humans to more easily manipulate and develop code as a more human-readable language, as opposed to low-level programming languages, intended specifically for machines as binary numbers, which of course can be extraordinarily difficult for humans to program in. At IBM in 1959, Herbert Geleitner built the geometry theorem prover. This algorithm was able to prove theorems that many math students found to be extremely tricky. And in 1961, Simon and Newell developed the General Problem Solver, or GPS. This algorithm was designed to imitate human problem solving, and it was the first to embody this idea of thinking humanly as one of the AI definition categories from the start of this lecture. In 1976, they also developed the physical symbol system hypothesis, which demonstrated that a physical symbol system, such as a programming language, has the necessary and sufficient means for general artificial intelligence. Working at the Cornell Aeronautical Laboratory in 1958, Frank Rosenblatt developed the perceptron as an extension of the early neural network idea. This was the first computer to learn new skills by trial and error. Here, the perceptron could not only make decisions, but could update weights in order to learn for prediction or classification based on experience. This, of course, became very important to the field of machine learning. And keep in mind, of course, that the hardware behind all this early work was extremely primitive, and of course, limiting in the development of these new ideas. At the bottom of the screen, you can find a link to a video about perceptron research from the 50s and 60s. In 1963 at Stanford, John McCarthy founded the first artificial intelligence lab. Their work emphasized general-purpose methods for logical reasoning. In 1966, Charles Rosen developed Shaky at the Stanford Research Institute. Shaky was the first electronic person and the first general-purpose mobile robot to be able to reason about its own actions. Shaky was also programmed in Lisp. At MIT in 1966, Joseph Weizenbaum created ELIZA, a pioneering chatbot that represented an early natural language processing computer program, and it was the first program capable of attempting the Turing test. You can try out a demo of ELIZA at the link found at the bottom of this slide. Next, AI research gets hit by a dose of reality, 1966 to 1979. Stuart Russell once stated, "From the beginning, AI researchers were not shy about making predictions of their coming successes." This statement hints at the early hype that was generated around AI at the time, which were quickly faced by some hard realities. For example, early AI systems had limited knowledge of the subject matter that was needed to solve problems. For example, some early attempts at translation systems in the Sputnik era were failures, as it was quickly discovered that accurate translation requires a huge amount of background knowledge, for example in the form of a knowledge base. Another issue was that there were limitations on the structures used to generate intelligent behavior. In 1969, Marvin Minsky and Papert pointed out that perceptrons of the time could only represent linear functions. This was because early perceptrons only included a single neural layer. The inability for researchers to get around this issue at the time led to a drying up of neural network research funding. And another major issue identified by James Lighthill in 1973 was the intractability of many real-world problems. Some researchers naively believed that scaling up to larger problems was simply a hardware limitation. Unfortunately, just because a solution can be represented doesn't mean that your system can actually learn it. Those aforementioned hard realities, along with limited computer processing power, data storage capacity, and network availability, as well as the realization of the true complexity of real-world problems, all set the stage for the first AI winter. Ultimately, the limited applicability of AI at the time led to funding pullback. This included the 1973 Lighthill Report, which was a devastating critique by the UK government that led to the near-total withdrawal of support for AI research in British universities, as well as DARPA cuts in 1974, which reflected similar funding cuts occurring in the United States as researchers failed to deliver on promises of machine translation and speech recognition. Ultimately, the hype in AI was not supported by enough actionable substance. Next, we have the emergence of knowledge-based systems in AI, from 1972 to 1979. Knowledge-based systems are largely synonymous with expert systems. These are computer systems that emulate the decision-making ability of a human expert. These systems can solve complex problems by reasoning through bodies of knowledge represented mainly by if-then rules, rather than through conventional procedural code. Expert systems were among the first truly successful forms of artificial intelligence software. In this schematic, we see an expert system that's made up of a knowledge base, an inference engine, and a user interface to create an automated system for storing expert knowledge and using that knowledge to automatically make decisions. Up till this point in time, most of AI research focused on general-purpose reasoning systems, which turned out to be a very lofty goal. But at this time, such systems started to be seen as weak methods because they couldn't scale to large or difficult problems. An alternative way of thinking was to come up with powerful methods that could use domain-specific knowledge and allowed for larger reasoning steps for more narrow areas of expertise. In 1969, Feigenbaum and Buchanan created Dendril, which was an expert system to identify unknown organic molecules by analyzing their mass spectra and using knowledge of chemistry. As a result, Feigenbaum is seen as the father of expert systems. In 1972, de Dombasle, a British physician, developed an expert system for the diagnosis of acute abdominal pain, but unfortunately went unnoticed by the AI community of that time. In 1976, Shortliff, Feigenbaum, and Buchanan developed Mycin, an expert system for the diagnosis of blood-borne infectious diseases. It was made up of 450 expert rules and was uniquely capable of dealing with uncertainty. This system was demonstrated to perform just as well as some experts and considerably better than many junior doctors. Some other expert systems of the time included ones that came out of the University of Pittsburgh. Here they developed Internist I, a general medicine diagnosis program. This algorithm was designed to capture the expertise of just one man, a clinician named Jack Myers. Another expert system they developed was called Caduceus. It was designed to improve on Mycin, which was focused just on blood-borne infections. Instead, Caduceus embraced all of internal medicine and could eventually diagnose up to 1,000 different diseases. Outside of medical applications, expert systems were also used by the military, including the Air Operations Division, which used rule-based expert systems for combat and training simulators, mission management aids, and support systems for tactical decision-making. Next, we move on to AI becoming an industry, 1980 to 1986. At this point in time, people started to realize that AI might actually be able to be used to save money or turn a larger profit. In 1981, the Japanese started the Fifth Generation Project, a 10-year plan to build intelligent computers running Prolog. Prolog was an early logic programming language. In response, the US formed the Microelectronics and Computer Technology Corporation. Both groups focused on chip design and human interface research. Around the same time, in response to the Alvey Report, the British started reinstating artificial intelligence funding. In all three countries, the goals were extremely ambitious and ultimately would never be reached. However, there were many success stories. In 1982, the Digital Equipment Corporation developed R1, an expert system for configuring computers. By 1986, R1 was saving the company about $40 million a year, and by 1988, the company had 40 different expert systems deployed. Also in 1988, the company DuPont had 100 expert systems in use and another 500 in development. It was estimated that these expert systems were saving the company at least $10 million a year. By this point, billions of dollars had been invested in expert systems, vision systems, robots, software, and hardware related to AI. And nearly every US corporation was using or investigating expert systems. The mid-1980s also saw a resurgence of neural network research interest. At least 4 groups reinvented the idea of backpropagation. This has become a crucial part of learning more complex neural networks, such as feed-forward neural networks, for supervised learning. However, the idea for backpropagation originally came from Bryson and Ho in 1969. In 1986, Terence Sejnowski developed NetTalk, a system that learns to read text aloud. This work also inspired the subdiscipline of AI referred to as connectionism, as a strategy for approximating human neural process using simple artificial neural networks. Today, multi-layer perceptrons are the commonly illustrated paradigm of connectionism. Connectionism is a bottom-up AI paradigm, in contrast with the more traditional top-down AI paradigm of symbolic reasoning. Now we move on to AI adopting the scientific method, 1987 to 1995. Unfortunately, the field of AI reached its second winter, extending from about 1988 to the mid-90s. This was due to factors such as the limitations of if-then reasoning becoming more apparent. For example, expert systems, while successful, were also generally very expensive and time-consuming to build, as well as difficult to maintain or adapt to novel information. Furthermore, many companies fell by the wayside as a result of failing to deliver on extravagant promises, such as those made by Japan's fifth-generation computer project, which failed to deliver on goals of holding conversations, interpreting images, and achieving human-like reasoning. As a result, AI funding and interest were again reduced. From the late 80s to early 90s, AI research again experienced some shifting perspectives. Another quote by Stuart Russell, "AI was founded in part as a rebellion against the limitations of existing fields like control theory and statistics, but now it's embracing those fields." At this point in time, there was a new emphasis emerging in artificial intelligence research as researchers started to embrace the scientific method. There were now expectations in AI research that hypotheses had to be subjected to rigorous empirical experiments. Results also needed to be analyzed statistically, as well as be reproducible. In 1990, Pearl and Cheeseman brought together probability theory and AI to give us Bayesian networks, which could learn from experience and combine the best of classical AI and neural networks into one idea. In the 1980s, Pearl, Hovitz, and Heckerman developed normative expert systems. These systems could act rationally according to the laws of decision theory, instead of trying to imitate them through the steps of human experts. The Windows operating system of the 1990s included several of these expert systems for diagnostic problem correction. Some other landmark applications in the 90s included work at IBM by Gerald Tesaro, who developed TD-Gammon, which was a neural network that demonstrated the advantage of using reinforcement learning. In 1993, the worldwide RoboCup initiative was begun, where here developers built soccer-playing autonomous robots that competed against each other. In 1995, Vladimir Vapnik developed the support vector machine algorithm, another key tool in the machine learning toolkit. And in 1997, IBM developed Deep Blue, a chess-playing computer that ultimately defeated world champion Garry Kasparov. Next, we move on to the emergence of intelligent agents, 1995 to the present. An intelligent agent is an autonomous entity that acts towards achieving goals upon its environment. It can observe its environment using sensors or perceptrons, and it can act on the environment with effectors and actuators. Intelligent agents can either learn or use pre-programmed knowledge to achieve their goals. Such agents can be simple or complex. For example, a simple one might be a reflex machine such as a thermostat, while a complex one might be something like a self-driving car. Let's take a look at some of the early successful agents that were developed. Newell, Laird, and Rosenblum developed SOAR, a virtual agent. The SOAR project had the goal of developing the fixed computational building blocks necessary for general intelligent agents. In 2002, the iRobot company introduced the Roomba, an autonomous vacuum cleaner that could navigate basic obstacles. In 2004, DARPA introduced the first challenge for autonomous vehicles. As part of this challenge, Stanford's vehicle Stanley self-drove across 132 miles of desert. Also in 2004, NASA's Spirit rover explored the surface of Mars. And in 2009, Google developed the first self-driving car designed to handle urban environments, and it drove successfully on a California freeway. This project later evolved into Project Waymo, that led to the self-driving Waymo taxis currently driving around my neighborhood here in West Hollywood, California. Now we'll discuss the age of big data in AI, 2001 to the present. Everything we've discussed until now has emphasized the algorithm as the object of study. However, often in the era of big data, it makes more sense to worry about the data instead of the algorithm. Specifically, while many modern algorithms can often achieve similar performance on a given task, data gathering and preparation considerations usually have a massive impact on downstream performance. In 2009, Halvey described the knowledge bottleneck, which is a problem regarding how to express all the knowledge a system needs to reason with. He proposed that maybe this could be solved by learning methods rather than having to hard code all of that knowledge through knowledge engineering. Another artificial intelligence fixture of the 2010s was that of IBM Watson. Watson was a supercomputer that in 2011 defeated the world's best Jeopardy players. Watson used a specialized architecture called DeepQA that could understand natural language, generate hypotheses, score evidence, and rank confidence. In 2013, Watson was adapted for utilization management decisions in lung cancer treatment at Memorial Sloan Kettering Cancer Center. And in 2015, IBM launched the Watson Health Division, promising to revolutionize medicine by acting as a super expert assistant for doctors. However, researchers noticed that Watson reflected the bias of trainers at specific hospitals and struggled to read different electronic health record formats from different hospitals, which led to high implementation costs. Watson was also characterized as a black box AI, giving predictions and recommendations without a clear, intuitive explanation of why. This led to a lack of trust, particularly in the medical field. Ultimately, in 2022, Watson Health was sold and rebranded as Merative, leading to an overall cautionary tale. Now we move on to the deep learning revolution of AI, from 2012 to the present. In the early 2010s, the availability of data as big data, hardware in the form of GPUs, backpropagation, and new algorithm architectures fired up the neural network theories of the 1980s. Deep learning is a specialized subset of the machine learning field that utilizes multi-layered artificial neural networks to identify complex patterns in large datasets. Here we can see a relatively simple schematic of a deep learning algorithm, characterized by having a larger number of hidden layers. Now let's look at some early deep learning advancements from the 2010s. Starting in 2011, products like Siri, Google Now, Cortana, and Alexa were introduced that used speech recognition to answer questions and perform simple tasks. In 2012, AlexNet and ImageNet were introduced as deep learning neural network architectures capable of smashing records in image recognition. In 2014, Facebook created facial recognition software called DeepFace that can recognize human faces with near-human accuracy. And in 2016, Google's DeepMind AI defeated Lee Sedol at the game AlphaGo, a game with more possible moves than atoms in the universe. Their AI system achieved this using a combination of reinforcement learning and Monte Carlo tree search. Later, a 2017 paper titled "Attention is All You Need" was published that as of early 2026 has over 200,000 citations. And this paper introduced the transformer architecture of deep learning, which allowed AI to process text in parallel and understand long-range context. Also in 2017, the startup company Vicarious developed a system that could beat CAPTCHA and reCAPTCHA in a new version of the Turing test, using a recursive cortical network. And in 2018, the company Alibaba developed a language processing program that was able to outscore Stanford students on a reading comprehension test. And then there's AlphaFold, which was developed by Google DeepMind and is considered one of the most significant landmarks in the history of AI. This is because AlphaFold took the field from the realm of games and digital media into the realm of fundamental physical science. In 2018, AlphaFold 1 showed promise, and in 2020, AlphaFold 2 was able to predict protein structures with atomic accuracy, matching the results of expensive, months-long lab experiments like X-ray crystallography in just minutes. In 2022, the AlphaFold protein structure database was released that included predicted structures for nearly all 200 million proteins known to science. This led to the winning of the 2024 Nobel Prize in Chemistry by Dennis Hassabis and John Jumper, the leads of the AlphaFold team. And most recently, in 2024, AlphaFold 3 was released with the ability to predict the structures and interactions of all of life's molecules, including DNA, RNA, and ligands. And lastly, we'll discuss the generative era of AI, from 2020 to the present. Most recently, we've entered an era where AI can create high-fidelity text, images, video, and more. The term generative AI is a broadly reaching term referring to any AI system capable of creating new content rather than just analyzing or classifying existing data. We can generally differentiate generative models from discriminative models, where the former models the joint probability of all observations X and target variables Y, while the latter models the conditional probability of a target Y given an observation X. Foundation models are a specific type of generative AI. These are single, massive models trained on a vast amount of data that can be adapted or fine-tuned to a wide range of downstream tasks. Foundation models represent a fundamental paradigm shift in how artificial intelligence systems are built. We can think of them as the base layer serving as a foundation upon which all other applications can be built. And lastly here, we'll define large language models, or LLMs, which are a specific type of foundation model that is focused on natural language processing. Well-known examples of large language models include ChatGPT-4, Claude, Llama 3, and Gemini. Touching on generative AI landmarks of the 2020s thus far, in 2020, GPT-3 showed that scaling models to billions of parameters led to emerging properties like zero-shot learning. From 2021 to 2024, versions of DALL-E emerged, which launched the text-to-image revolution. In 2022, ChatGPT brought AI into the hands of the general public, triggering a massive shift in how we think about search, writing, and education. ChatGPT was based on the Generative Pre-trained Transformer, or GPT, model, and was considered by some to be the most successful product launch in history, spawning an entire industry for generative AI. And lastly, from 2023 to 2024, we've seen multimodal breakthroughs, or models like GPT-4o and Gemini 1.5 Pro that can see, hear, and speak simultaneously in real time. This figure gives a recent overview of the generative AI model landscape, separated into different application themes. At the top, we can see major players in conversational AI and large language models, including ChatGPT, Gemini, Claude, Grok, Meta AI, and DeepSeek. Looking ahead, there are many possibilities for the future of AI. Most immediately, there is surging interest in the area of so-called agentic AI, shifting to AI systems that don't just answer questions, but can execute complex multi-step workflows automatically. There's also interest in physical AI and embodied intelligence. Currently, AI is still largely trapped in a screen. The next decade may see the convergence of large language models and robotics, giving AI a body that understands the laws of physics. Further, there's strong interest in reasoning and transparent AI. Today's models are fast and intuitive, but prone to what are called hallucinations. Future research and development is also focused on making artificial intelligence slow down and think, as well as provide transparency through explanation and model interpretability. Further, there is much emphasis on AI driving scientific discovery. Building on the success of AlphaFold, AI is poised to become a primary engine for basic science. And lastly, focus on efficiency and sustainable AI. As the energy demands of data centers skyrocket, research and development is also pivoting towards green AI to reduce costs and environmental impact. This lecture has focused on the broad history of artificial intelligence, but there are many other related histories that run parallel to artificial intelligence, including computer hardware, computer software, artificial life, robotics, machine learning, and natural language processing. I'll leave you with this simple schematic illustration as a summary of this lecture on the history of artificial intelligence. I'm Ryan Urbanowitz, and thanks for joining me for this lecture. Stay skeptical, curious, and creative.